Hello everyone, this is Radha Hawk presenting my findings for Physics 2211 Lab 5, the Human Rocket. In October 2012, Felix Baumgartner stepped out of a helium balloon capsule at 39,045 meters above Earth, higher than commercial planes fly, and free fell towards the ground. In this lab, I used flow script and Newton's second law to model his fall computationally, and I investigated how realistic versus simplified atmospheric models affect the predicted motion. The central physics question is, does Felix actually break the speed of sound? The answer turns out to depend entirely on how we model the atmosphere, which is exactly what we're investigating in this two-part investigation. The key new force in this lab compared to previous labs is aerodynamic drag. Unlike gravity, drag is non-constant. It grows with the square of speed, and in part 2, it also varies with position because air density itself changes with altitude. This makes part 2 a doubly non-constant force problem. The other forces that we used are shown here. I chose CD is equal to 0.7 because that's the standard estimate for a person in pressure suit in the free fall position, not perfectly streamlined and not perfectly flat either. The mass of 118 kg accounts for Felix's body plus the pressure suit and equipment. These are approximations but physically reasonable ones. So what changes between part 1 and part 2? We only changed the formula for drag. So this one change, whether air density is constant or position dependent, turns out to be the entire story of whether Felix can break the sound barrier. In part 1, the atmosphere is so thick from the start that drag is huge, immediately capping his speed. In part 2, the near vacuum speed at high altitude means drag is nearly zero at the start, letting him accelerate much further. Here you can see the code that I used for part 1, which we will discuss in more depth. The visualization, as you can see on the right, shows that Felix as a science sphere falling vertically. The green box at the bottom is the ground and the faint yellow marker is at 25,000 meter altitude, a visual reference for approximately where someone would cross the sound barrier if they were fast enough. Here we have the force calculation. Newton's second law in the loop is identical to what we used in lab 3 and lab 4. Compute the net force, update velocity, update position. The only difference is what forces we include and how we compute them. And here you have the result graphs. So at first we have the speed versus time, where you can see that it reaches terminal velocity almost instantly. And then you have the altitude versus time, which again is a nearly perfect linear descent because of constant speed. Finally, we have our kinetic energy versus time graph, where it reaches terminal velocity almost immediately. The constant atmospheric model gives a physically unrealistic result because the sea level air density creates massive drag from the moment he steps off the capsule. In reality, at 39,045 meters, the atmosphere is nearly a vacuum, which is why part 2 is the more physically interesting model. And here we have the code for part 2, which we will again discuss in more depth. And let's take a look at the simulation that the code produced. Perfect. Now, we use the barometric formula for air density, which tells that air density falls off exponentially with altitude. At Felix's jump altitude, there is less than 1% of sea level air. This is what makes the real fall so dramatic. The loop structure is identical to part 1. This is intentional. The physics framework of Newton's second law doesn't change. What changes is the drag force calculation with just one extra line at the top, which you can see. This single line is what makes part 2 physically realistic. And here we have the results from the graph. First, we have speed versus time. It tells the story in 3 acts. Free acceleration in near vacuum, a peak near the sound barrier, then deceleration as the thickening atmosphere increasingly overpowers gravity. This bell-shaped curve is completely absent from part 1. It only appears when we model the atmosphere realistically. For the result of altitude versus time, Felix, you can see that this is no longer linear due to changing speed. As per overall result, Felix nearly breaks the sound barrier. Our peak speed over here, as you can see, is around 340 meters per second, which is within 1% of 343 meters per second. Then we have the graphs of density versus time and kinetic energy versus time. The kinetic energy versus time is obviously reflected of the speed versus time graph, and air density is growing exponentially as Felix distance. This is the reaches part of the lab. The drag force peaks after the speed peak because even as Felix slows down, the density is still rising. The competing effects of falling speed and rising density produce the drag peak delay, which you can only understand by plotting all 3 quantities together. Now, this direct comparison of part 1 versus part 2 makes it vivid. They are the same simulation with only one changed line of code, yet they produce wildly different results. Peak speed differs by a factor of 5, fall time differs by nearly 4 minutes. This is what physically realistic modeling looks like. This is the key physical insight. Terminal velocity is not fixed number when the atmosphere is not uniform. In part 2, Felix effectively changes a shrinking terminal velocity as it falls into thicker air. Finally, we have our 3 what-if questions. So, what if Felix jumped from 50,000 meters instead of 39,000? Well, the air density would be even lower at the start, so even less initial drag would accelerate even faster and would likely break the sound barrier. What if we ignore the drag force entirely? Well, that is first of all physically impossible, and Felix would accelerate at the acceleration of free fall continuously. So after 260 seconds, we would only get 2548 meters per second of speed. Now, what if we double CD more? If we did that, then our drag would be doubled at all altitudes, terminal velocity would be even lower, peak speed would be lower, and would definitely not touch the sound barrier. This shows that the cross-sectional area and suit design matter. So what were the sources of error and assumptions? These approximations are what physicists call a simplified model. We capture the dominant physics while ignoring second-order effects. The barometric formula is actually quite accurate for the troposphere and stratosphere combined, making part 2 a solid approximation, though you can see the few sources of error listed in the table. In conclusion, this graph demonstrates that physics modeling is only as good as its assumptions. The atmosphere matters, and once we model it realistically, the physics changes entirely. Felix's real jump was a triumph of both human courage and physics understanding.